Hi, folks. My name is Arul Verma, and this week we're going to be talking about shared state and mutex. So our goal for today is to talk about shared state, the idea of sharing data across threads, and why that's important, specifically in the form of the reader-writer problem. And we'll also go over mutual exclusions, or mutexes, and atomic operations, specifically in the form of the art, which is used to get around mutexes and the issues that come with mutex. So we've previously talked about sending and sharing data between threads. So we've talked about how you can pass messages between thread using the MPSC or multiple producer single consumer library. And we've also kind of briefly mentioned that sending messages is very easy and it's very intuitive at times, but sharing memory within threads is not as intuitive. Specifically, sharing data is something that's very difficult because of how threads work. So obviously we can pass messages using the MPSC library and MPSC sender and MPSC receiver respectively. But how exactly do we share data? So the concept of sharing data between threads is through something called a mutex lock. Mutex locks allow you to take advantage of how Rust's type stream system works and a lot of the advanced programming concepts that come in systems in order to make sure that data can be shared without causing any data conflicts. So let's start by talking about the reader-writer problem. So the reader-writer problem starts very much like this. Say we have some piece of data in memory. If multiple people want to write to that data simultaneously, data integrity will not be preserved because someone's write of data will be overwritten. Say we have some data, some integer that stores the value 8. Now if two writers come and at the same time, because they're simultaneous threads, they write, one writes 8 to 9 and the other writes 8 to 12. Eventually, 8 will end up as, let's say, 12. The 9 will get overwritten. And when the original writer comes back to read that data, they'll read incorrect data. At the same time, we have to think about if someone's reading while someone is writing. If the reader came to read that value of A and the writer writes 9, they are reading incorrect data, the reader, because the data that they were originally going to read has been overwritten. So the question begs itself, how do we preserve data integrity when simultaneous actions are happening? The answer to this is through a concept called the reader-writer problem called a mutex. This is essentially that you can only have a singular writer at a given time. You can have as many readers as you want at a given time, and you cannot have a simultaneous writer and a reader. So how does this work in the context of programming? Because this is a very theoretical approach to data and data memory. So this comes in the form of mutexes. Mutex is an abbreviation for the term mutual exclusion. Mutual meaning they're common, and exclusion meaning that it is exclusive to one person, it is unique, and you can deny access to others. So a mutex is essentially the concept that you could only one thread can access some data at a given time. So a great example of this is essentially the microphone solution. Say you have a panel of speakers at a conference, and only one person can speak at the same time. The rest of the speakers at the panel are your readers. They can only hear what the current speaker is saying. The microphone gives access to a singular speaker to voice their thoughts, hence they being the writer. The microphone acts as a mutex. It controls how many people can speak at the same time, while also making sure that everyone else can only pay attention to a single person at a given time. So for a mutex to work, a thread must first signal that it wants to take access to the data that the mutex is holding. So it must ask to try and acquire the mutex lock on the data. A lock is a part of the mutex inherently. In Rust, locks are part of the mutex data structure. And all they do is they keep track of who has exclusive access to data at any given time. Only a singular thread can hold a lock at a given time. This is because when no one has a lock, that data is readable. So it is in public readable space. But the moment someone acquires a lock, that data becomes a written data. So data has to be completely written, and the lock has to be released before someone else can read it or write to it. So one place that mutexes differ in Rust compared to other languages is that normally in C and C++, which is something you'll see in CS341, mutexes are used to guard sections of code because these sections of code cannot be ran simultaneously, particularly when you're editing data. This is mostly due to how C and C++ handle memory differently compared to Rust. Because of how Rust works and how Rust handles memory uniquely, in the sense that we have our own ownership and borrowing laws, and that data is automatically released from scope after it stopped being used. This memory difference makes it such that mutexes and mutex locks do not work as intuitively to guard sections of code. Rather, it's more intuitive to make sure that the mutex guards data. And this difference is just that the mutex will guard data and it'll just lock and unlock that data to allow it to be used by multiple people or a singular person at a given time. While in other languages, all the mutex does is it serves as a barrier to entry, so only one thread can pass through the mutex at a given time. So this is some of the syntax for a mutex. So you use the mutex : mu, and then you put your data inside in order to create a new mutex to provide mutual exclusion for your threads. And then you have your mutex.lock. Your mutex.lock creates your lock for your given mutex. And if you use the .unwrap after it, it returns a mutex guard for the data. And all this really does is that it makes sure that other people cannot attempt to acquire another mutex. Now, the question that you must be asking is, if you lock, shouldn't there also be an unlock? Well, in Rust, mutexes don't need to be unlocked. As we said, because of how Rust memory works, mutexes can be handled a little bit more uniquely. And the reason for this is that the mutex guard that's returned from your mutex.lock, the moment it goes out of scope, it is automatically dropped from memory and the mutex immediately unlocks the data. So this means that you don't actually need to worry about unlocking your mutexes in Rust. And this is one less load that's removed from you as the programmer. So here we have an example of our mutexes on our left. So we have a very simple mutex creation. We just use mutex : u on an integer of which is just 0, and we're letting that mutex be data. And then we say for 0 in 10, we spawn our threads and we move data into our threads. And then from 0 in 20, we try and acquire a lock. We try and increment the data by 1 and then unlock by going out of scope. And then after this, the other threads can attempt to increment our data. Now, one thing you might have realized that's kind of counterintuitive is the nature of how mutex works. Mutex essentially is exclusive use of data, right? But when we move it into the thread, we're giving every thread access to that data. So it's no longer exclusive. That exclusiveness is gone. Every thread has access to that data. The only time exclusivity is displayed is when we lock it here. So this doesn't really make sense. And the compiler tells us that you created a mutex, but you're not copying it anywhere. So everyone's trying to access the same mutex. And because you're using move, it's not exclusive anymore. Your mutex is not exclusive and unique to a singular thread, because only a single thread can have ownership of some value with how mutexes work. So this code would actually break. So now we have to bring up a concept called atomicity. And atomicity is something we'll get into more later. But first, let's think about just how non-atomic or just normal sequences of events occur with two threads. So say we have some data 0, and we have two threads running simultaneously. And all they do is they increment our data by 1. So our T1, our thread 1, will load our data into its register, and we get data equals 0 in our register, which is our register is just where we store our data in hardware. Our second thread will load the same data into its register, load data equals 0 into its register. And now it also has data equals 0. Now thread 1 increments its data by 1. So now it gets its data 0 becomes data 1. And thread 2 does the same thing. It takes its data 0 and it increments it by 1. So now it has data 1. Now thread 1 writes its data back into memory. So now we have data equals 1 in our memory. And then thread 2 attempts to write its data as well, and it writes it back into memory, and we have data equals 1 in memory. So despite the fact that we had two threads, both of which are incrementing data by 1, we only actually, in reality, outputted data equals 1. We only incremented data by 1 because of the nature of how threads work. Because threads do things simultaneously, actions like loading data into our register, and then the incrementation of that data does not get registered, or I say registered, but does not get like updated for our second thread. Our second thread is not aware that thread 1 incremented data and made it 2, or sorry, made it 1, and it doesn't know that it has to make it 2 next. So with atomic operations, atomic simply means that we can give that data access to multiple people, and we'll get more into that in a second. But atomic operations, We want writes to be immediate and to be unique so that other readers and writers will always see the correct value because by the time they load data into register, the thread that accessed the data prior will have already written. So this in between is what we call atomic. And this is what the ARC or arc is. The arc is essentially a smart pointer, and we call it its arc, but the full form is atomic reference count smart pointer. And what it does is it keeps account of the number of references to the data inside the pointer. And we only drop the data when the number of references inside is 0. So this it may not be fully clear, but let me give more details. So what we do is we wrap a mutex with the arc class, and we create a smart pointer for it. And the reason we can do this is because of how pointers work, essentially, right? We talked previously about how Rust has memory safety in place because of how if you have multiple pointers pointing to the same piece of data, and one of the pointers goes out of scope, all of your pointers end up going out of scope, and your data gets overwritten. So the atomic reference counter kind of abuses this concept. It creates multiple references of itself or it creates multiple copies of itself that all reference the same data, the same mutex, essentially. So when we want to give multiple threads access to the same data, we create an arc pointer and we just copy it over and over for each thread. So now each thread has its own exclusive smart pointer that references the same mutex lock. And this lets the arc essentially give access of the data to multiple threads without violating our exclusivity. And the way the arc also makes sure that it avoids going out of scope and deleting our data is it only goes out of scope when the number of references is 0. So how does it keep track of the number of references? Well, it's fairly simple actually. Every time the clone function is called for arc, it automatically increments a numeric that just keeps track of the number of original pointer references. After that number hits 0, as each one goes out of scope, only then will the entire mutex go out of scope itself. And so this means mutex guards can be dropped individually, and that will make sure our arc decrements its counter for the number of references in a single access session. So this is the concept of atomic. When accessing or mutating a property that is atomic, it means that only one read or write operation can be performed at a single time. And you can keep it thread safe by keeping track of the number of references. So I know I briefly showed you this slide, but we'll go more in detail now. So arc is also its own unique class. You create an arc using the : new function, and it creates a smart pointer that wraps data essentially. And generally, this data is a mutex in and of itself because you want to protect the data. You can use .clone in order to create a new arc smart pointer that references the same data that the original pointer references. And it's the separate structure, but it's the exact same reference. And this also at the same time increments the number of references to the data in our arc. This way, when a single arc goes out of scope, or a single pointer, I should say, sorry, the arc knows to decrement the number of references inside it, and it only goes out of scope when all of its individual instances go out of scope. So what you can do is you can pass a clone pointer to your thread, so you can continue to reuse and clone the original arc when passing your data to threads. So let's take a look. This is essentially how to use arcs in order to fix the code we had before. So now we have the same data. We've created our mutex on our 0, and we create an arc to wrap around our mutex. What this does is it essentially allows us to create a pointer for our mutex so multiple people can access it by using our clone. We say let clone equals data.clone, and we move it into our thread. And for 0 to 20 inside our clone.lock, we can acquire a lock on our mutex by dereferencing, incrementing, and then the mutex guard will go out of scope, so the arc will decrement, and it'll know that, oh, okay, our data has been freed and someone else can use it. So the next thread will go, it'll access the data, it'll acquire a lock, increment, the lock will go out of scope, and then someone else can access the lock. And if you run this code and you use the .join .unwrap and everything, you'll get 200 because our data will increment 20 times for a single thread for each of our 10 threads. And that's the concept of arcs and mutex. Thank you all for listening. If you have any questions, feel free to reach out to us over Discord. This is a very complex concept, and we know that it'll be very difficult. So we tried and giving you guys some easier homeworks on shared state and kind of to get you guys introduced to the concept of using mutexes and arcs and the MPSC and everything. We hope that really helps out. And of course, if you have any questions, feel free to reach out to any of our staff. We'd love to help you out. Have a great day, guys.